in our previous lecture we were discussing about some fundamental physical and mathematical considerations for natural convection. Now today what we will do is we will perform some order of magnitude or scaling analysis to unveil some important physics associated with natural convection. So we will, as a model problem, consider the natural convection order of magnitude analysis or scaling analysis. With an example of natural convection boundary layer adjacent to a vertical flat plate. So this is exactly the situation that we discussed in the previous lecture, but we will now try to get some deeper insight. I mean, in the previous lecture we had a broad understanding, and now we will try to get a deeper insight. So this is the vertical flat plate, and we set up the coordinate axis such that this is x axis and this is y axis. So what are the boundary layer equations? First, the continuity equation, the y momentum equation that is important. So u del v del x these are the boundary layer equations. And these equations are coupled because you have to know the temperature field to solve the velocity field. These sets of equations we discussed in the previous lecture. Now we will take it up from there and try to make an assessment of the various parameters. Let us say that we make a scaling analysis of the continuity equation first. So what is the order of magnitude of del u del x? Let us say uc is the characteristic velocity along x. Let us say that the height of the plate is h. So del u del x, what is this? See, you are analyzing the natural convection, that means where you are analyzing it, within what boundary layer. See, when we say boundary layer equations, there is a little bit of sense of vagueness about it, because it does not tell whether it is hydrodynamic or thermal. I mean, one obvious reason is they are coupled, but when you are writing these equations or analyzing these equations, what is your domain of interest? Is it hydrodynamic boundary layer or thermal boundary layer? It is the thermal boundary layer. The reason is that temperature gradients are existing only within the thermal boundary layer, and that temperature gradient is actually driving the flow. It is T minus T infinity. So, if you look at this source term, this is T minus T infinity. So, T is different from T infinity only within the thermal boundary layer. So, the important body force in the momentum equation comes into picture only within the thermal boundary layer. That does not mean that the hydrodynamic boundary layer and thermal boundary layer thickness is the same, because the fluid also has its inertia. So, when it attains its peak velocity, not that just outside the thermal boundary layer it suddenly comes down to 0. So, it takes a bit of a distance to come down to 0. So, that is because the fluid has its inertia. So, even when the heating or cooling effect is stopped, still there is some motion. Therefore, hydrodynamic and thermal boundary layers are not of the same thickness, but what is important is that the hydrodynamic is not the continuity equation in the hydrodynamic boundary layer that is of importance for this boundary layer analysis, but it is the continuity equation analyzed within the thermal boundary layer. So, UC divided by delta T, right, not delta. This is, what is the order of magnitude of this? Let us say Vc is the characteristic velocity along y, Vc divided by h. So, as we have discussed earlier, if these two terms are of the same order of magnitude, then what it means is that UC is of the order of Vc into delta T by h. So, if delta T is much less than h, then the velocity scale along x is much less than velocity scale along y, but it is still not 0, right. Then we will analyze the energy equation before entering into the momentum equation. What is the order of magnitude of this? You see, what is, this is some characteristic temperature difference by some characteristic length. What is the characteristic temperature difference? T wall minus T infinity. That is the triggering temperature difference for heat transfer, right. So, in shorthand notation we write it as delta T. So, delta capital T is nothing but T wall minus T infinity. So, UC into delta T by delta T, this is of the order of Vc into delta T by h, and this is of the order of alpha delta T by delta T square. And UC, in place of UC we can write Vc delta T by h. So, you can see that these two terms are of the same order of magnitude. You can see that this is philosophically such an important inference that from the momentum equation, from the energy equation, from any physical scenario, we have seen that when we come to the boundary layer analysis, in the advection terms no term is dominating with respect to the other until and unless one is identically 0. Like for internal flow the situation is different, because for fully developed flow V is identically equal to 0, But if V is not identically equal to 0, then no matter how small the u or V, whatever, how small is it, you will see that these two terms are of equal order of magnitude. This is something which is not very intuitive. So, these two terms together is of the order of Vc delta t by h, that is of the order of alpha delta t by delta t square. So, delta t square, or you can write Vc is of the order of alpha h by delta t square. See, why we have come up with an expression for Vc is because this is what is our matter of interest, that is, see, try to understand it practically. You are investing by heating a plate, heating a vertical plate. So, always, just like any business, you want a return of investment. So, in heat transfer business, in natural convection, your return of investment is what flow you are getting out of this temperature gradient that you are creating. Okay. So, this is the scale of velocity that you are getting by creating the temperature difference delta T, and interestingly that temperature difference delta T does not appear anywhere in this expression, right. That is again something which is not very intuitive. So, we will keep this expression in consideration. Now, we will come into the momentum equation. So, just to give you a perspective, this term physically is what? This is inertia, this is viscous, and this is buoyancy. So, let us try to get order of magnitudes of these three terms. So, what is the order of magnitude of the inertia term? So, you can calculate any one of these, because we have already seen that they will be eventually the same order of magnitude. So, this is, it is more straightforward because this does not involve delta t. So, Vc square by h. This, what is the order of magnitude of this? Nu, this is a very important thing. See, we are making our analysis within the thermal boundary layer. So, it is delta T and not delta, although this is momentum equation. When we will be analyzing this momentum equation for the hydrodynamic boundary layer, then this will be replaced by delta, but we are using the momentum equation for analyzing the physical situation within the thermal boundary layer, and that is why this is delta T and not delta. And this is of the order of G beta Now, can you tell that out of these three forces there is at least one force which you expect to be important in natural convection? What is that? Buoyancy, because this force is the driving force for natural convection. Now, given that this force is an important parameter for natural convection, the question is out of the other two forces which one is dominating, because out of the other two forces whatever is dominating that will compete with this, right. So we will find out inertia by buoyancy and viscous by buoyancy and see which is more and which is less. So inertia by buoyancy. So inertia by buoyancy is of the order of now in place of Vc you can write alpha h by delta t square. So this is alpha square h square by delta t to the power 4 by h g beta delta t. So one h gets cancelled because here you have delta t to the power 4. So to make it compatible and non-dimensionalized, the numerator should have h to the power 4, then we will get h by delta t whole to the power 4. So for that you have to multiply both numerator and denominator by h cube. So this becomes g beta delta t h cube by nu alpha into h by delta t to the power 4 into nu by alpha. Why we have done this is because again this is our by the time so familiar non-dimensional number, the Prandtl number. This is non-dimensional. So this is another non-dimensional number, a very similar non-dimensional number we discussed in the previous lecture, that was g beta delta t h cube by nu square, Grashof number, and this is g beta delta t h cube by nu alpha, this is called as Rayleigh number. So so this you can write as g beta delta t h cube by nu square into nu by alpha. So Rayleigh number is nothing but Grashof number into Prandtl number. Which one? No, that is all right. I am just writing this one g beta delta t h cube by nu alpha. Huh? Oh, this term we were talking about. So alpha by nu, sorry, not nu by alpha, right, alpha by nu. But I am just talking about this Rayleigh number, this term. Okay, so Rayleigh number is, again you can see this is Grashof number into Prandtl number. So this, anyway this we can write g beta delta t h cube by nu alpha, so 1 by Rayleigh number into 1 by Prandtl number, this is 1 by Prandtl number into h by delta t to the power 4, right. So this is inertia by buoyancy. Let us calculate viscous by buoyancy. viscous by buoyancy, viscous force nu Vc by delta T square divided by G beta delta T. What was Vc? Alpha H by delta T square, right? So this is nu into alpha into H by delta T to the power 4 G beta delta T. So this you can write it as G beta delta T H cube by nu alpha into H by delta T to the power 4, right. So this is of the order of 1 by Rayleigh number into H by delta T to the power 4. Now can you tell that by this analysis how can we figure out that which force will compete with buoyancy in the thermal boundary layer? Is it inertia force or the viscous force? Depends on Prandtl number, right? Because you see the difference between inertia by buoyancy and viscous by buoyancy is the factor 1 by Prandtl number in the inertia by buoyancy. The remaining factors are the same, that is 1 by Rayleigh number into H by delta T to the power 4, they are the same, only difference is 1 by Prandtl number. So again the situation boils down to whether Prandtl number is much greater than 1 or Prandtl number much less than 1. So we will consider the first case when Prandtl number much greater than 1. If Prandtl number is much greater than 1, then inertia by buoyancy is much less than viscous by buoyancy. Right? Because other factors are the same. That means which forces are competing? Viscous and buoyancy. Within which boundary layer? Thermal boundary layer. So viscous is of the order of buoyancy means 1 by Rayleigh number into H by delta T to the power 4 is of the order of 1, right. These two are of the same order. That means delta T by H is equal to Rayleigh number is of the order of Rayleigh number to the power minus 1/4. Right? From this delta T by H to the power 4 is of the order of Rayleigh number to the power minus 1. So delta T by H is of the order of Rayleigh number to the power minus 1/4. So just like the assumption, the boundary layer assumption that in the boundary layer theory, for forced convection what was the assumption? For hydrodynamic boundary layer, delta much less than L, whatever we consider the length of the plate, delta much less than that. For thermal boundary layer, delta T much less than L. So here also for natural convection, delta T much less than H will be our assumption. Why? Because if you recall the energy equation, we have neglected del square T del Y square as compared to del square T del X square. That assumption is based on the fact that delta T is much less than H. So delta T is much less than H only when the Rayleigh number is large, right. Just like for the hydrodynamic boundary layer analysis for flow over a flat plate is valid for large Reynolds number. Similarly, here the situation is coming for large Rayleigh number. For thermal boundary layer in forced convection, it is Reynolds number into Prandtl number, that. So here, but it is basically related to Reynolds number to the power n into Prandtl number to the power m, where n and m may be two different coefficients. So here also it may depend on Rayleigh number to the power n into Prandtl number to the power m. Here Prandtl number is not coming into the picture, but for the other case where Prandtl number much less than 1, Prandtl number will come into the picture, because you can see the existence of Prandtl number in the denominator. We will come into that subsequently, but before that we will try to find out what is the Nusselt number. Again, in any problem of convection, it is a Nusselt number that is our matter of interest. So if this is the plate and this is the y axis, at the wall we can write minus k del T del y at wall is equal to H into T wall minus T infinity, right. Nusselt number is this H expressed in a non-dimensional form. So what is the order of magnitude of this? Yes, what is the order of magnitude of this? K the characteristic temperature gradient takes place within the thermal boundary layer, and that is T wall minus T infinity by the thickness of the thermal boundary layer, and this is H delta T. This is exactly equal to H delta T, you need not put as order, because this is H and this is delta T. So these two terms must balance each other, so that you can write H delta T by K is of the order of 1. This inference does not depend on the value of Prandtl number. So now the Nusselt number, which is H by K based on the length H, is equal to H delta T by K into H by delta T. So this is H delta T by K is of the order of 1, and H by delta T is of the order of Rayleigh number to the power 1/4. That means Nusselt number is of the order of Rayleigh number to the power 1/4. If you do very rigorous mathematical analysis, at the end what new thing you will gain is you will still get this with a constant C, that which you are not able to capture through this order of magnitude analysis. So you will get Nusselt number is equal to some constant into Rayleigh number to the power 1/4. That constant's value you can get by more detailed analysis, but the entire physics you can capture through this except for the value of that constant.